This time, we are going to prove that the limit of the product of a constant c and sequence b sub n is equal to this product of the same constant c and the limit of b sub n, which is L. So this is still part of proving limit theorems using definition as part of the review and sequences in series for preparation for real analysis. So here's the statement. Let C be any real number and B sub n be convergent sequence of real numbers with the limit of B sub n be equal to L. Then we are going to show that the limit again of the product of constant C and B sub n is equal to the product of the same C times the limit of B sub n, which is L. So we are going to use here a definition. We're going to look into the processes. The first one is, of course, if possible, we can express this expression into the form of definition and the presence of a absolute value for the specific limit specific to this portion here, and then later on provide bounds for our epsilon, because epsilon will be there to make sure that we will return to our goal. Of course, part of our proof is to show what is to be proven. So here, let's start with our proof. Let epsilon be greater than 0. So epsilon is already here. So what we need to do is this. We must show that there exists an n which is integer such that if n is greater than that n, then we could show, per definition, that this notation, the constant c times b sub n, the sequence, minus c times L is less than that said epsilon. So this is our target. If we could reach this, then we can now invoke that this is true. But part of that again is to make sure that we can express this into a form where we involve this limit, and then later on we need to come up with how do we properly bound our notation using any possible form so that we can ensure that epsilon will be present at the end. Not epsilon something, but epsilon itself as part of the definition. So here's the thing. In the previous two videos, in the limit theorems involved in the sum and difference of two sequences which are equal to the corresponding sum or difference of their corresponding limits, here we were able to use triangle inequality during that time. Here, we may not need triangle inequality here. Okay? But of course, let's look into that. Okay, let's break this if possible. Note that if we have the absolute value of c times b sub n minus c times L, we can factor c, making sure that we have b sub n minus L. We can see that this is already an indication of this form here. Okay, for the limit of b sub n, which is equal to L. We can still further break this according to one of the theorems on absolute value. If we have the absolute value of the product of two expressions, then we can make them as product of two absolute value expressions. So you have here and that. This is by one of the theorems in our lesson. Okay, so once we break them, take note, this has been already recorded. Again, this denotes to this form. So we'll have that later. Okay, that's part of our form. So since we're able to express the form into a form where there is a corresponding limit, so let's look into the notations now where we express epsilon into a form. So we have here, let me change this into black. So since the limit of b sub n is equal to L, then there exists n, which is an integer, such that if n is greater than n, okay, then we will have here the absolute value of b sub n minus L be equal to, let's say, this should be an expression where later on, when combined to this, will return to our epsilon. In the previous videos, using sum and difference, we're able to use epsilon over 2 because there are two of them. Okay, what do you think would be the proper form here? Take note that this is just part of here, in hoping that later on when this will be revisited, whatever be the result, will only come out with epsilon. Here's my hint. Let me use here epsilon over the absolute value of c. Okay, so that later on, once this is expressed into this form, we can cancel absolute value of C, then leaving epsilon alone. Okay, that's part of your strategy, and how do you make sure that your bounds will return to your epsilon, or the term here is epsilon control. Okay, now take note, for this case, make sure that C is not equal to 0. Because if C is equal to 0, then this is undefined. So what happens if C is equal to 0, even when we are sure that C is any real number, which also denotes 0? Part of the understanding here is, yes, we will be using this, making sure that C is not equal to 0, but still the possibility of 0 is still here, because that's part of the definition. However, if you're going to consider your limit here, if you're going to consider C equal to 0 here, what happens to the sequence is that it would be a constant sequence of 0. And obviously, it would be converging to 0 times L, which is still 0. So basically, 0 is still accepted, and 0 is still part of our statement here, because if C is equal to 0, automatically, yes, it's convergent, and it's converging to 0. Okay, hopefully you have agreed with that, because this will surely be true if C is equal to 0. It's just that for this portion, we will not be allowing 0 rather, so that C will not, or this expression will not be identified. But don't worry, C is 0. C being 0 is still acceptable and part of our statement. But it's just that in this proof, we will not be accepting C equal to 0, and it's still okay. Okay. Now after this, we can now return. So if n is greater than or equal to n, we'll be using this now. So you will have here C times B sub n minus C times L is equal to, again, directly providing here absolute value of C, absolute value of B sub n minus L. Don't worry if I were not able to pass through this and jump into that, because we already shown that earlier. Okay, and this is, okay, sorry for that. Okay, since absolute value of C is still there, but this is already identified by this form, expression with epsilon. Okay. So this entire form, this is still less than the absolute value of C, because that's part of the property of inequality. You will have this 2, so it will not change the inequality because that's absolute value. And then times epsilon over the absolute value of C, which is the indication of this. Okay, which is equal to epsilon, because you can cancel that out. Let me remove the cancellation so that it will be clear. Okay, so from this, from here going here, we have established that the absolute value of C times B sub n minus C times L is less than epsilon. And take note, this is what we would like to show here. And as mentioned earlier, once we reach to that, we can now invoke that this is true. Okay, so this was made possible because of this interpretation. Don't be confused, as mentioned in the previous videos, epsilon over 2 that we used in the previous 2 videos is not all the time true, because it depends on how you are going to express your expression with epsilon, so that epsilon will come out later on as part of your proof. So since this is already okay, since epsilon greater than 0 is arbitrary, then we conclude that the limit now, because this is already okay, the limit of the product of a real number C times your sequence B sub n is equal to the same real number C times the limit of B sub n, which is L. This is the proof for this limit theorem. Again, this might be different from the previous 2, but make sure that you really know how to make sure that your bounds are okay in order for you to return to the epsilon that you're targeting as part of the definition. Thank you very much for watching.